Another view to solve the motif finding problem, we can convert this problem into the medium string problem. And in the medium string problem, we calculate the Hamming distances between the two DNA sequences. The Hamming distances is the distances means the difference between the two DNA sequences of equal length, and at a specific position the elements they within the two equal DNA sequence or strings, they have the different elements at particular location. So the number of elements that are different will be known as the Hamming distances. If it is two elements that are different within the two equal length strings, then the Hamming distance will be 2. And if the differences is within the 3 elements, then the Hamming distance will be 3, and so on. So I have already told that we have to calculate the Hamming distance between the two Elmers V and W. For example, this is the V Elmer and this is the W Elmer. So we can see in the first column both have A and A, adenine, adenine. But in the second column we see in the V Elmer there is a thymine, but in the same position in the W Elmer there is a C. So T and C are different, so that's why it is written between these T and C across. In the third column both are same, thymine, thymine. In the fourth column again, in the V Elmer it is G, and in the W it is C. So that's why this cross is written. But in the fifth and sixth column, both the elements within each column are same. So in this case, in the two Elmer V and W, the Hamming score is 2. One is here and one is here. Now we suppose that the S, that is the starting point of each of the DNA fragments, S1, S2 to ST, is an array of some DNA sequence, and V is the Elmer. We will modify this notation a little bit and use this Hamming distance Vs to denote the total Hamming distance between V and Elmers. So we will represent this after modification. The starting position S, that is the Hamming distance Vs, is denoted by sigma T1 I is equal to 1 dH Vs1. So we, up till now, we must be knowing what is meant by this equation. So we have solved this equation many times up till now. So in this equation, dHVSI is the Hamming distance between V and Elmers that starts at a very specific position SI. SI could be any number. In the ith DNA sequence, ith means in the specific DNA sequence. So we will get the total distance vDNA, that is minimum number of S, and Hamming distance in VMER, and that will start at the position S. Finding the total distance vDNA is a simple problem. First, one has to find the best match for V. In the first DNA sequence, as we have seen, we have 7, 8, 10 sequences, and we have to find the best match. That is a position minimizing the Hamming distance. It means the differences between the two elements in the two string must be minimized. There should be no differences. If there is no differences, then the Hamming distance will be minimized, and that will be minimized for 1 is less than is equal to S1 and S1 is less than n minus 1 plus 1. So we have to move the two strings one by one, and we have to move by the value of 1 so that we could find the minimum Hamming distance. Then the best match in the second sequence will be calculated, and this process will be continued. So that is the minimum is taken over all possible starting position S. And finally we define the median total distance VDNA, that is the minimization is performed. So we have to calculate this process for all the 4 L strings of the V of L length. So 4L means adenine, thymine, guanine, cytosine, and we have a specific Elmer length of the DNA sequence. So here we can see we can also design an algorithm to find out the median string within the DNA sequence. So for this purpose we have to input a T into N. T is the DNA sequences, number of DNA sequence, and N is the size of the motif within the DNA sequence, and L is the length of the pattern to find. This is the same type of algorithm we have seen in the previous module, and the output will be a string of V of L nucleotides, means it's Elmer, that minimize the total distance, that is VDNA, over all strings of that length. So we will get the double minimization by using this algorithm, and we have finding a string of V that minimize the total distance VDNA, which is in turn the smallest distance among all choices that are starting from S. We have seen that all within the DNA sequence the specific motif will start at different positions within the promoter region. So we have to calculate this one, the minimum distance between these motifs within the DNA sequences. So we have seen earlier that this is a double minimization process. One minimization is here, all choices of Elmers in the V, and the second minimization is all choices starting as position S. So after this double minimization we will get the minimum Hamming score. So the interesting thing here is that despite the fact that median string problem is the minimization problem and the motif finding problem is the maximization problem, but these two problems are computationally equal. So we will see here later how they are equal. So for example, we assume that there is S to be the set of starting position with consensus score of sDNA, and let W means the length of the Elmer string of the corresponding profile. Then Hamming distance WS will be L into T minus score sDNA. So from this figure we can calculate both the motif finding problem and the median string problem. So we have already said that the median string problem is the minimization problem and the motif finding problem is maximization problem. So here we can see this is the profile, and the Hamming distance between the consensus string W and each of these 7 implanted pattern is 2. It means that we can see here in each of the sequence these 2 in black color, that is the Hamming distance of this sequence, means 2, and in the second sequence again 2, and third 2. So in all of the 7 sequence the Hamming distance is 2. So we can calculate very easily the Hamming distance WS. So 2 is the W and S means the number of sequences, they are 7, so it calculated as 14. So in the other way, in the motif finding problem, we can see here the 7 is the sequences of DNA, and 8 is the size of the motif, and we have to multiply it. It comes out to be 56, and we have to minus all these red. So these red are 42 in number, and if we minus 56 from 42, again the answer will be 14. So we have proved that the median string problem and the motif finding problems, although they are very different in nature, but they are computationally equal.